All right. Okay. Hello and welcome everyone to the next talk of the morning. So the next talk would be by Neha Prabhu, who is now in University of Pune, but until few days ago was in IISER Pune. And she will be talking about a joint equidistribution theorem with applications to extremal primes.
Okay.
Neha?
Thank you, Bhaskar, for the introduction, and thanks to the organizers for giving me this opportunity to speak in this symposium. So Bhaskar just mentioned, but even though I'm not in IISER right now, this deserves a talk in the ISE IISER symposium because I'm a former IISER student, and it so happens that Amita Malik is a former ISC student. She did her master's there, so it's work coming out of two former alumni. Okay, so today's my talk today is about a joint distribution theorem, but the elements in the joint distribution theorem, or rather the motivation for it, comes from something called extremal primes. So I will start with introducing what those are. And to do that, I'll start with the notion of equidistribution of a sequence. So Kaninika in her talk gave a definition in terms of equidistributions of sets. So I'll go a step back and talk about just a sequence. So a sequence of real numbers xn in 0, 1 is said to be uniformly distributed or equidistributed if for every subinterval AB in 0, 1, the following holds. So the proportion of n up to capital N of the elements of your sequence lying in the chosen interval AB tends to the length of this chosen interval AB. Okay, so in some sense, it's saying that it's spread out evenly across all subintervals. So for example, the sequence of fractional parts of n alpha, where alpha is a fixed irrational number, is equidistributed. And the fractional parts of log n is not equidistributed. So sorry about that. More generally, a sequence is equidistributed with respect to a measure. So this is viewing this as a Lebesgue measure. One can look at an arbitrary measure and redefine the equidistribution with respect to this measure as replacing the right-hand side by the integral over the integral d mu. Okay, so this will be important because we'll be choosing a measure, which is the Sato-Tate measure. Okay, so now the Sato-Tate conjecture for elliptic curves is as follows. So you look at a curve y squared is equals x cubed plus ax plus b. This is the Weierstrass form, and a and b are chosen so that you don't have a singular curve. And you reduce those coefficients mod a prime p, where p is again a prime not dividing the discriminant. The number of fp points on the curve is given by p plus 1 minus e sub a of p. And this quantity a sub e of p is of interest and has been studied over the last few decades. Hasse's theorem tells us that if you normalize it by square root of p, then this sequence lies in the interval -2, 2. So one can ask how, as primes vary, how do they sit inside this interval? Around 1960, Sato and Tate independently conjectured the distribution of the sequence, and that was known as a Sato-Tate conjecture. So in the case of elliptic curves, if E is a non-CM elliptic curve, and you count the proportion of primes for which the normalized sequence elements lie in a chosen interval of -2, 2, then the proportion of such primes tends to a certain measure of the interval, which is known as the Sato-Tate measure. So this is normalized for -2, 2. You might see different functions, but that depending on what interval you're taking, if you're taking it from -1, 1, it looks slightly different and so on. But this is the conjecture, and what was proved in a series of papers by Clausel, Harris, Shepard, Batten, and Taylor. So just as an example, Here is the histogram plot showing the distribution of a sub e of p divided by square root of p for this particular curve, which is known to be non-CM, up to 1,000,000 primes. So you can see that there's a semicircle shape emerging, and that's exactly the shape of the distribution. It's also called as a semicircle measure in the literature. Okay, so what we want to focus on today is what's happening at the endpoints. So clearly at the endpoints, you see that there are fewer primes that accumulate. And so it's interesting to see if we can say something precise. And this brings me to the definition of an extremal prime. An extremal prime for an elliptic curve E is a prime of good reduction, satisfying a sub e of p is plus or minus the greatest integer of 2 square root of p. Okay, that's by Hasse's theorem. We know that those are the endpoints of the interval it can lie in. And so you see how often it can actually take that value in integer value. The study of extremal primes is rather recent. So in around 2017, Kevin James and his co-authors conjectured that the asymptotic for non-CM curves would be a constant times x to the quarter over log x. And if he has complex multiplication, then it's x to the 3/4. So if you see the distribution in the case of CM curves, it is more uniform and sort of tapers upwards towards the endpoint. So you expect a larger proportion in when you have complex multiplication. But in the case of non-CM curves, as we saw, it's much fewer at the ends than in the middle. So the asymptotic is x to the 1/4 over log x. Okay, and just a quick definition that an elliptic curve has complex multiplication if its endomorphism ring is bigger than z. Okay, so progress towards this conjecture. The asymptotic for CM curves was proved by James and Pollack in 2017. In the case of non-CM curves, the asymptotic was shown to hold on average by Giberson in 2017. So by on average, I mean that instead of fixing an elliptic curve, you vary the curves where you take the average over little a and little b, the parameters in the Weierstrass equation, you let them grow in a certain, with respect to x in a certain way and show the asymptotic. Upper bounds, so the next best thing you can do this is for CM curves. For non-CM curves, for a single elliptic curve, the asymptotic is open. And the next best thing one tries to do is see if you can do upper bounds. So towards this, an upper bound of x to the half was proved by a bunch of us in 2020. Later in 2021, an unconditional bound, this was under GRH, and GRH for symmetric power L functions. Then in 2021, an unconditional upper bound of x log x squared divided by log x squared was proved by Gaffney, Thorner, and Wang. So you see that there is just less than a log x power saving, the less than log saving. But recently, so this is work which is in the process of being written up, I've been able to prove that you can get an unconditional upper bound of x to the 3/4 e to the minus c log square root of log x for some computable constant c. So this is work towards the extremal primes conjecture. We investigate in this talk a related quantity. So for L prime, we ask what can we say about the number of primes such that the extremality condition is satisfied modulo L. Okay, so this is inspired from the work of Sayre on upper bounds for Lang-Trotter conjecture, where he considered similar. Okay, so for Lang-Trotter, you want this to be equal to some A. E does not divide NE. So this is the Lang-Trotter conjecture, where you fix an integer A. So this is a fixed integer, and you ask what this is what this proportion is, and this is supposed to be some constant times x to the half over log x. So in some sense, it's very similar. The extremal primes has a similar thing. There's a constant, and then there's an x to the quarter here. But then here you have a to be constant, but we have the number depending on the prime p. So it varies with p, so it's a different question. Anyway, so Sayre considered a sub e of p congruent to a mod L in his work. So that was one of the inspirations for this this quantity, to consider extremal primes mod L. Okay, so we prove that if you take a non-CM elliptic curve E, rational elliptic curve, and assume that GRH holds for the Dedekind zeta function of the L torsions fields Q adjoin E of L over Q. So Q adjoin E of L is just the field obtained by adjoining the coordinates of all the L torsion points of E to Q. Okay, so given an elliptic curve, you know that there's like an addition law, and so L torsion just means L times a point is identity of the group curve. Okay, so the result we have is that if we have a certain bound on L satisfied in terms of x, then the number of primes such that the extremal condition is satisfied mod L is equal to x over log x plus an error term. And this error term, this growth ensures that this is a true error term because we wanted to isolate this main term. Okay, so this is the consequence of a joint distribution, which will come shortly. So let's start with the proof, and then the joint distribution will appear in the middle. Okay, so if you want to count the number of primes for which a sub b of p is 2 root p mod L, we say, okay, let's sum over all the residue classes and look at those primes for which the a sub b of p and integer part of 2 square root of p is congruent to the same a mod L, and then you sum over L, a. Here we denote square bracket as the integer part and the fractional part with the curly braces. Now the condition 2 root p congruent to a mod L can be translated as follows. So you take the fractional part and you see that that has to lie between a over L and a plus 1 over L. How is this coming? Well, if we know that the integer 2 square root of p is kl plus a, then the 2 root p itself should be that integer plus its fractional part, and then you divide by L to see that you get an integer, and then this becomes a fractional part. And so that has to lie between a over L and a plus 1 over L. Okay, so that's fairly straightforward. But unpacking the condition a sub b of p congruent to a mod L is less straightforward. Okay, so let E of L denote the L torsion subgroup of E of Q bar. The action of the Galois group, Abdul Galois group, on the automorphisms of EL can be expressed using a Galois representation. Okay, so there is a certain Galois representation, and Sayre proved that this is surjective for all but finitely many primes L. Okay, and moreover, we also know that this L torsion field is the fixed field in Q bar of the kernel of this Galois representation. Okay, so now use Galois theory. We know that if H is a normal subgroup, then we have that the Galois group of the fixed field over F would be the total Galois group mod H. And so using the surjectivity, we know that the Galois group mod the kernel should be, and the kernel should be isomorphic to the Galois group of the fixed field of the kernel, which was nothing but the L torsion field. And so this tells us that the Galois group of Q adjoint EL over Q is isomorphic to GL to FL. Okay, so why is this pertinent? Well, there is a special automorphism called the Frobenius automorphism sitting in there. And it turns out that the image of this Frobenius is given by, the characteristic polynomial of the image is given by this quadratic. And the trace appears to be A sub B of B. Okay, so the trace of the Frobenius automorphism is A sub B of P mod L. And so if you look at the union of conjugacy classes of trace A, this finally tells us that the condition A sub B of P congruent to A mod L is true if and only if the Frobenius automorphism viewed as an element of GL2FL sits in one of these, is an element of the conjugacy class of trace A. Okay, so we've unpacked the two conditions. So going back, this is what we started with. We wanted to count the number of primes for which the extremality is satisfied mod L. And breaking down the two congruences gives us the Frobenius at P sitting in a certain conjugacy class, or rather union of conjugacy classes, and the fractional part of 2 root P mod divided by L to lie in a certain interval. Okay, now, so these two appear as special cases of theorems already known in the literature. For example, Frobenius sitting in a conjugacy class, if you're a number theorist, you would immediately think of the Chebotarev Density Theorem. And so we know, so I've only mentioned it. Okay, yeah. So the quantity sigma p prime such that sigma p belong to C of A. So I've omitted the fact that P should be unramified so that it's cleaner. But yeah, there is a condition here. But anyway, so if you take any finite Galois extension of number fields, you know that this quantity is the proportion of the size of a conjugacy class divided by the Galois group size of the Galois group times pi of x plus some error. Okay, this was proved. The first error term was given by Laguerre and Orlisco in 1977. And on the other hand, if you want to study distribution of fractional parts of p to the theta, maybe with some constant tagging along, so sitting in an interval, that is can be studied using the equidistribution of such sequences, which is studied by many people and variants of it. But the simplest thing is that the distribution is uniform. So if you look at the primes up to x for which the fractional part of p to the theta is less than delta, where delta is fixed in 0, 1, then this is proportional to the size of the interval and plus an error term. And this error term is something what a lot of people have. So several papers have worked on trying to improve the error or include something like an alpha here, or make it alpha p to the theta plus b, and so on. So these two are both very well studied areas. And for what we want something that satisfies both a Chebotarev type condition and fractional parts sitting in an interval. And so we require a joint distribution theorem. Okay, so we have sigma p in C, and we have some kind of alpha p to theta less than delta. And we want this to have the product. So individually, it was delta pi x and C over G times pi x. And we prove that together they give delta C over G pi x plus an error, of course, under GRH. So more precisely, you take a finite Galois extension L over Q with Galois group G, and let NL be the size of the extension. Let alpha be a positive real number, and you take a subinterval of 0, 1 of length delta. You fix a theta in 0 and 1. So we prove a more general, so what we need for our application is just theta equal to half. But of course, since we're proving a joint distribution theorem, we might as well prove it in more generality. Now define pi x cg to be the number of primes up to x, which do not divide the discriminant, so that the Frobenius at P belongs to your chosen conjugacy class or a union of conjugacy classes. And the assume GRH for the Dedekind zeta function of L over K. Then there's a condition, assume a certain condition relating all these parameters floating around. And the main thing is that we do get the main term, delta pi x cg, plus an error term. And again, this condition is just to ensure that all this is smaller than delta pi x cg. Okay, so it's looks a little technical, but the main thing is that we get what we want. And what we've done is kept the dependence on NL and alpha and delta and so on. So the only thing that the constant I should have written could depend on is theta. But if one wants, you can actually find out the dependence of theta as well. It was messy enough as it is, so we just treated it as a constant. Okay, so this is the theorem, but I will not prove the theorem, but just use it to finish the bound for extremal primes, the model. Okay, so in our case, we have L over K as the L-torsion field over Q. The Galois group, as we saw from the work of Serre, is GL2FL. C over G is the size of the union of conjugacy classes of trace A, which if you compute, that's also well known, and divided by G, you get 1 over L plus O 1 over L squared. NL is the size of the extension, so that's just the size of GL2FL. For us, alpha p to the theta, alpha is 2 over L and theta is half. And the interval delta 1, delta 2 is A over L, A plus 1 over L. Okay, so the size of the interval delta is 1 over L. So we just go back and plug this in. So here is where we left off before describing the joint distribution result. And so for each A, you get the main term coming from the Chebotarev Density Theorem, the joint distribution, and the error term. And then we apply the Chebotarev density, the effective version for this. And so we get x over L log x plus the error after we sum over all the A mod L. Okay, and so this was the result for extremal primes. Okay, some remarks on the joint distribution result. So recall that what we were studying is that you count the number of primes for which the trace of the Frobenius sits inside a conjugacy class and a fractional part sits inside a certain interval. So this can also be viewed as a theorem in a set of other results proved in a similar with similar flavor. So one is that of combining the Chebotarev density theorem with the distribution of Carmichael numbers. So a Carmichael number is a composite number n such that b to the n is b mod n for all integers b. Okay, so you look at the Fermat's little theorem that holds whenever n is prime, but if that congruence holds for composite numbers, such a number is called a Carmichael number. And I think the first Carmichael number is 561, if I remember correctly. Okay, and in 2013, Banks, Gulaulu, and Eager showed that there are infinitely many Carmichael numbers n, which are solely composed of primes p satisfying a Chebotarev condition. Okay, so by this, I mean that sigma p belongs to C in a finite Galois extension of number fields. And more recently, in 2015, Gulaulu and Yildirim proved a joint distribution of Piasecki-Shapiro prime satisfying a Chebotarev condition. So a Piasecki-Shapiro prime is a prime number of the form integer part of n to the c, where c is some positive real number and n is in positive integer. Okay, so and there's one more which I think I did not upload the latest version of the slides. So here is like, okay, so these two results talk about Chebotarev combined with something to do with the a different condition on primes. But there's another joint distribution, another line of joint distribution results where you look at the distribution of fractional parts and impose another condition. And in that direction, there have been something like you look at number of primes less than x, such that the fractional part of p to the half is less than delta, and p belongs to some set PR, where PR is the number of prime, and PR is a set of primes such that p plus 2 is composed of exactly r prime factors. So with counted with multiplicity. And so there's been work relating to this. So, and one last comment, you might wonder why one cares about the fractional parts of p to the half. Well, this is connected to the infinitude of primes of the form n squared plus 1. So it's true that this is less than p to the, I think, minus 1 over 4 infinitely often, if and only if n squared plus 1 is prime infinitely often. Okay, so this was where the interest in these kind of distribution results. And this is not even known under GRH. The best is 1 over minus 1 over quarter plus delta, I think. Anyway, this is so if one could prove this, one would prove this highly unsolved, long unsolved problem. So just trying to sell that this distribution result brings a lot of very interesting results in the literature together. Okay, and I will end my talk with that. Thank you for your attention.
All right, let's thank Neha. And okay, guys, so are there any questions? Okay, if not, let's thank Neha again. And we will, I think basically we can we will basically start the next talk in a few minutes. So, you have like 2-3 minute break. All right, Hariram, can you